Take a moment now and think about a device that pumps fluids around or transports fluids in some way that has flow through some kind of pipe or equivalent to a pipe, but that pipe is not circular. So how often in your daily life do you come up with flow through a pipe where that pipe is not circular in its cross-section? Trying to come up with many options? I can only really come up with a few. I guess I have a furnace in my house, and that has rectangular ducts. In grad school I did some microfluidics, and that sometimes has square or rectangular channels. But almost always we have flow through circular. Flow through circular pipes. So this can be things from like flow in our blood vessels in our bodies, flow in tubing that we use to make medical devices or bioreactors or anything else, flow in our water mains for our civil engineering systems in our buildings. We have flow through circular pipes all the time. And as we've learned in bioengineering, it's oftentimes very useful to think about flow through pipes, and in flow through pipes we might want connections between things like velocity and shear stress, volumetric flow rates, and sort of all of these parameters. We also might want connections between the pressure drop in pipes, things like that, right? So is there a connection between pressure drop and velocity, shear stress, volumetric flow rate? How are all these things connected? As engineers, we need to be able to mathematically connect these things. We need to be able to predict things like pressure drops for particular velocities or particular volumetric flow rates. And we said, hey, and last time when we were doing the blood oxygenator problem, we said, hey, shells could basically give us a lot of these relationships by deriving what this velocity profile is. So shells, the problem-solving strategy, allows us to derive velocity profiles, and once you have the velocity profile, then that informs a lot of these other things. So shells give us a velocity profile, and once we have a velocity profile, that unlocks all of these awesome things. So what is our goal today? Our goal today is to consider flow through a pipe, flow through a circular pipe, and our goal is to derive this velocity profile via shells. So when we think about deriving velocity profiles, we oftentimes want to break it down into a series of steps that we can use to solve this problem. So let's take a moment now to outline the steps that we're going to take to solve this flow through a pipe problem to derive the velocity profile. So just to look ahead at where we're going, we're looking to basically say, hey, we have some circular pipe in a region that's not too close to the entrance of that pipe. We know we're going to get this velocity profile that will look something like this, right? Where right at the edge of the pipe, the fluid immediately adjacent to the pipe isn't moving, but we have some pressure pushing on one side of the fluid at one point harder than the other. We have a higher inlet pressure than our outlet pressure, and that basically drives the fluid through the pipe like this. So in previous problems, we basically had the clouds open up, and first Professor Lannin's face poked through and told you, this velocity profile is parabolic, but now we're looking to derive it on our own, and we can derive it using the following steps. So what is our strategy? So in this case, our first thing is to select an appropriate shell to basically define a micro control volume within this, and the micro control volume is going to have some infinitesimal dimensions, right? So select an appropriate shell, and when we select a shell, we'll typically do two what I'll call delta dimensions that will take infinitesimally small. And one of the dimensions is going to be in the direction of flow, and the other is going to be in the direction that flow varies. Then, for our next thing, we're going to apply conservation of mass. And what is this going to do? This is going to affirm that the flow is 1D. That the flow is one-dimensional. After that, we're going to apply conservation of momentum. And sometimes we might need to apply conservation of momentum in multiple directions. We'll see how that turns out this time, whether we'll need to do that or whether we'll need just one conservation of momentum direction. Then we'll conservation of momentum, and this will give us a differential. This will give us a differential equation, and usually it'll give you a differential equation involving shear stress in some way. And we'll define exactly which shear stress we're talking about once we get there. So we have this differential equation that involves shear stress in some way, oftentimes, but we're not looking for shear stress explicitly, we're looking to get this velocity profile. So oftentimes we can get a relationship between shear stress and velocities by applying a constitutive relationship. So for example, for Newtonian fluids, it would be tau is equal to minus mu times dv d something. And in this case, we're actually going to be working with cylindrical coordinates. So spoiler alert, it's going to be tau rz is going to be equal to minus mu dvz dr. So we'll apply some constitutive relationship here. Then finally, we're going to, once we apply this constitutive relationship, we'll end up with the differential equation not involving shear stress, but involving velocities. We'll solve the differential equation. And typically in the process of solving this differential equation, we'll integrate and apply boundary conditions. And sometimes we might integrate, sometimes we might integrate and then apply some boundary conditions and then integrate again and then apply some things, so we might bounce a little bit back and forth between these steps 4 and 5, or sort of glom them together in some ways, but these are two tasks that we'll need to do, although sometimes the order might vary a little bit. And then finally, once we solve the differential equation, integrate and apply our boundary conditions, we'll then have a velocity profile that will be super awesome. We could then hypothetically use this velocity to compute stuff we care about. Right, so we could basically, if we have a velocity profile, we could put it in, we could take its derivative to get shear stress, or we could integrate that velocity profile across a cross-sectional area to get volumetric flow rate or something like that, right? So, shear stress, volumetric flow rate, etc. So this is the plan. We've outlined the 6 steps that we're going to use to solve this, and we're going to do all of them for this pipe. We're going to do shells, but the shell is going to be a little bit trickier than the last one we did, in that we're now dealing with the cylindrical geometry to help deal with the circular geometry of the pipe. So let's go ahead with selecting an appropriate shell, and also, as part of selecting an appropriate shell, we'll also define our coordinate system too. So we'll define our coordinate system in our shell. So let's go ahead and do that. Step 1. So when we think about a coordinate system, I have some tube that I have flow going through. Hypothetically, we could use a Cartesian coordinate system, x, y, z here, but usually when you're dealing with flow in circular pipes, it makes sense to use cylindrical coordinates. So what do I mean? Let's imagine we have a pipe right here, and in this pipe there's some center line like this. It's usually good to set the origin of your coordinate system along the center of the pipe. So let's define some variable r little r, which is essentially the coordinate that describes, you know, a part of our position of where we are in the pipe. And we can put that sort of in contrast to what I'll use as big R, which is the physical radius of the pipe itself, right? So we have some pipe, little r describes the position of some point, the radial position of some point within the pipe, in contrast to big R, which is the overall radius of the pipe right here. Then I can basically, then I can define another coordinate. We'll call it z, and z is basically the position, you know, the sort of axial position down the pipe, or in a sense the horizontal position of some point within the pipe. So r and z basically define where we are in the pipe. Additionally, we could define theta as essentially some, you know, like the angle, and basically r, theta, and z can fully define any point in this pipe here in a way similar to x, y, and z defining some other point in a Cartesian 3D space. So we have this here, r, z, and theta. Now let's go ahead and define our shell within this control volume. And in particular, for these problems, we generally want to choose 2 delta dimensions for these. We'll choose one in the direction of flow and another in the direction that flow varies. So in the direction of flow, right, we anticipate flow. Flow direction is in z, and the direction, the coordinate along flow variation is going to be r, right? So flow varies, right? So flow is in the direction of z, but it varies as our position with r. So we're going to choose r and z. So the dimensions of our shell, of our micro control volume, one of the dimensions is going to be delta z, and one of the dimensions is going to be delta r. So take a moment now, see how in this system, you know, what exactly would a little control volume look like? What would a shell look like with one of its dimensions being delta z and one of its dimensions being delta r? So take a moment now, pause and ponder. What would a shell look like with one of its dimensions as delta z and one of it's with delta r? Well, hopefully you've had a chance to pause and ponder. So delta r is essentially saying, you know, we're going to have part of our shell at some point, and part of our you know, one surface of our shell at r, one surface of our shell at r plus delta r, and they're going to be separated by a distance delta r. So what does that mean? Well, we're basically going to have a part of our shell look like this, where we'll have a concentric ring where the thickness of the ring is delta r. But of course, a ring isn't really a full volume, right? There's no volume of sort of like just a 2D ring. This ring also has a width or sort of a thickness delta z, right? So here's going to be our shell. It's this sort of circular ring right here that has a thickness delta r in this dimension and a thickness delta z in this dimension. So this is what we're gonna go ahead and do. All right, so now we've defined an appropriate shell, but I think actually I might have jumped the gun a little bit in defining this shell right here. I actually should, you know, kind of list a little bit more information that we're going to need to know to sort of solve this problem, and to help kind of, you know, give some more knowns than just the radius of the pipe, and also start building a list of assumptions that we're going to need in order to use this shell's approach and end up deriving this velocity profile that we expect to get right here. So what might be some assumptions that we need? Right, so it turns out that we only really get this velocity profile, you know, this so-called parabolic velocity profile that we're anticipating getting if we're dealing with steady flow Right, so we're going to assume the system steady. Strictly speaking, it is possible to derive what the velocity profile looks like for unsteady flows, but that's kind of like a graduate level fluids class, so we're not going to do that today. We're also going to assume that the flow is laminar. I know Smarter Every Day is definitely the king of laminar flow on YouTube, so I'll be the prince. Let's just deal with laminar flow right here. So what I mean by laminar, well, turbulent flow would sort of have, turbulent flow wouldn't really have this velocity profile. It would instead have something where there's a whole bunch of swirling eddies, and all of that's time varying. So turbulent flow is something that oftentimes we rely on experiments or computer simulations to help deal with. We can only really get nice pen and paper solutions for laminar flow, but laminar flow shows up all the time in biofluids, so this is useful enough in its own right. So we're just going to deal with laminar flow. Let's also deal with the case where the pipe is horizontal. So we'll just deal with that. Strictly speaking, we could have a vertical pipes, but that's just kind of throwing additional complication in, and I'm really looking for the relationship in this case between pressure and flow rates, sort of pressure driven flow through pipes rather than gravity driven flow through pipes. So we'll just restrict ourselves to horizontal tubes today. Let's also say that we have some fluid here and we know the properties of the fluid, right? So this fluid has some density and some viscosity. And if we're assuming a constant viscosity, that implies that we have a Newtonian fluid. And we'll also assume that the fluid is incompressible as well as homogeneous, such that density is equal to a constant as well. Where I guess it goes without saying that we're assuming that the walls of the cylinder are stationary and impermeable. Right, so strictly speaking, the walls of our blood vessels are actually slightly leaky. So sometimes fluid comes in and sometimes fluid exits into and out of the surface of walls of our blood vessels. Things like that. Under most circumstances, it's a pretty good, this is a pretty solid assumption that we're making right here. Right? And we're basically saying that there's some pressure driving flow. We essentially have some pressure here upstream, some pressure downstream here, and it's this pressure that's driving the flow right there. So, so there we have it. These are the assumptions that we're building so far into our model. All right, so what's up next? Well, I'd say we did a pretty good job selecting our shell and defining our coordinate system, and in that process, defining the shell, we kind of got to this here. Oh, there's one more assumption that we're going to need to deal with. We're going to assume that the flow isn't really swirling in the theta direction, right? We don't have some sort of like helical flow. Like when you take out the bathtub or flush the toilet, like the flow kind of swirls as it goes down the tube. We're going to assume we don't have any of that going on. And furthermore, that we don't have variation in theta, right? So we're going to assume there's no velocity in theta, nor variation with anything in theta. And this variation with anything in theta has a special name. We call it axisymmetric, in a sense that it's symmetric about the z-axis. So with these assumptions in mind, we might add to this list later on, but with these assumptions in mind, we can now go ahead and apply conservation of mass to our shell. All right, so what's that going to look like? Let's move on to 2, where we're applying conservation of mass. So conservation of mass, we have d dt of the integral over the volume of our shell of rho dv is equal to minus the integral over the surface of rho times v dot n dA. So this is the general form of conservation of mass. Of course, we have this control volume right here, so we need to break up this control volume into a couple of pieces. So take a moment now, pause and ponder. Can we make any simplifications to this system right off the bat? Well, perhaps we can, right? We assume the flow is steady, and if we're steady, we can get rid of the left-hand side that has this time derivative. So we can basically get rid of the left-hand side if we're steady. So what does this mean? This leaves just the right-hand side to kind of break up. So if we want to break up this integral over the whole surface of our control volume into a couple of pieces. So let's take a closer look at this control volume and think about what pieces we want to break up the surface into. All right, so I'm going to do a little color coding. Let's call this sort of upstream surface, we'll call this surface 1. Let's imagine I have this outer surface. We'll call that surface 2. I have this inner surface right here that I can solve surface 3, and not shown right here is the face that's opposite this face 1 right here. So, you know, downstream, on the downstream face, I have surface 4 as well, right? So basically I can break up my control volume into these 4 surfaces. Now, if I'm going to start thinking about this v dot n, I might need to make some assumptions about some of these velocities. So we already basically assumed we had no velocity in the theta direction. So what does this mean? So this no velocity in theta basically is saying that v in the theta direction is equal to 0. We know that, or we're strongly anticipating that our velocity in the z direction is non-zero. So, you know, vz is not 0. And if we're going to have to sort of go through this 1D, if we're going to be assuming that this is indeed a 1D flow, you know, vz is non-zero, so we're going to basically be assuming that vr is 0. What does that mean? I mean, that's pretty consistent with what we have here. You know, if we have vr, we're not going to have radial flow. You know, once we're sort of downstream of the entrance right here, you know, we can't really have radial flow, because that radial flow, you know, if it gets to the edge, where does it can go? You know, that flow can't go through the boundary right here. So, you know, this, we're basically assuming no radial velocity is essentially kind of part of our 1D assumption right here. So let's assume these things, and, you know, see where that gets us in terms of 1D. All right, so let's now think about breaking up the surface into these control volumes right here. All right, but before we can break up this surface, we oftentimes want to characterize our control volume a little bit. So I might think about, you know, if I'm going to compute these integrals, I might start thinking, you know, hey, what is going to be the volume of this control volume? What's going to be the upstream and downstream areas? So let's cross that bridge when we get there, when we get to some integrals. So let's do conservation of mass. So we have 0 is equal to minus an integral over surface 1 of rho, which we're assuming is a constant, times v dot n dA. So this surface 1 we're basically assuming is at some position z, and surface 2 we're basically saying is at z plus delta z, right? So we have some flow entering this green part of the surface, and I can call this flow that's entering the green part of the surface, I can call it vz at position z. And then I have some flow exiting the downstream face, and I can call this Vz at z plus delta z. Right, so there's a subscript z because it's flow in the z direction. Into surface 1, it's Vz at z, and out of surface 4, it's Vz at z plus delta z. So, so what is that? What is that going to look like? So we're going to have surface 1. We're going to have rho. V dot n for surface 1 is going to be minus Vz at z. dA. Then surface 2 is this outer surface right here. Actually, sorry, I'm gonna change the numbering a little bit to make it consistent with the notes. Sorry, I'm still gonna call the green surface 1. Sorry, I'm gonna change my numbering just because I wanna be consistent with what I have earlier. So we're gonna call green surface 1. We're gonna call the blue surface, the downstream surface, surface 2. We're going to call the outer surface, surface 4, and we're going to call that inner surface, surface 3. Sorry to change things on you, I just want to have it consistent with my notes so I don't make mistakes. So, upstream green, downstream blue, inner surface 3, red, outer surface orange right there. So surface 1 is this. Then we have our, then let's do surface 2. So we're still going to have rho, and V dot n for surface 2 is going to be positive Vz at z plus delta z dA. So that's surface 2. Then we'll have surface 3. Now, if I think, do I have any fluid entering or exiting surface 3? Well, we basically said, hey, if we're assuming that velocity is only in the z direction, in order to have mass flowing into or out of surface 3, we would need some non-zero VR. So what does that mean? We basically are going to have a 0 inside of or a 0 because v dot n for surface 3 is 0, right? We have flow going purely in the z direction, and the perpendicular to this surface would be sort of in the minus r direction. And the same goes for surface 4 as well. So what does that mean? Well, we can, if we make our delta r, this dimension is delta r. If we make our delta r arbitrarily small, we can neglect the fact that Vz, strictly speaking, kind of varies across this surface, right? We can make our shell calculously small in these directions. So even though, strictly speaking, velocity does vary, would vary from the inner part of this shell to the outer part of this ring, we can make this delta r arbitrarily small, so it doesn't appreciably vary. So what does that mean? We can basically pull this stuff out of the integrals, both here and here, and then once we pull out rho and these velocities, we're left with just integral dAs. If you're left with integral dAs, then that just becomes the area themselves. So what does this mean? We basically have 0 is equal to rho times Vz at z times whatever the area of 1 times the area of 1, and then we have minus rho Vz at z plus delta z times the area of whatever face 2 is, this downstream face. All right. Now we can formulate these areas. So what is that? So take a moment now, pause and ponder. What are these areas? What are the areas of these faces in terms of sort of some of the geometrical stuff that we've outlined? if we think about it, the area of this annulus, if we make this delta r arbitrarily small, is if we took this cylinder and kind of unwrapped it to a rectangle, where one of the dimensions of that rectangle is delta r, and the other is the circumference right here. So we basically say, hey, we have some ring. This ring is essentially at, the inner part of this ring is sort of at some position r. So these areas are basically going to be equal to delta r times the circumference of that inner ring, which would be 2 pi r. So the areas, both A1 and A2, the upstream and downstream ones are the same. Both A1 and A2 are delta r times 2 pi r. So what does that mean? Our conservation of mass gives us the following result. Well, I guess we can just divide everything through by density before we proceed too much. So we're left now with 0 is equal to Vz at z times delta r times 2 pi r minus Vz at z plus delta z times delta r times 2 pi r. And last time we said, once we got to a point like this, a useful strategy is to divide by the volume of our shell, or of our control volume. So in this case, we're basically dividing by, we'll take a moment now. What is, pause and ponder, what is the volume of this control volume? Well, hopefully you've done it. The volume of our CV is basically going to be, if we took this thing that now has some finite thickness and kind of unwrapped it into a rectangular prism, one of the dimensions of the rectangular prism would be the circumference, 2 pi r. Another dimension would be delta r, and then another dimension would be delta z. So in this case, the volume of the shell is equal to delta r times 2 pi r times delta z. So that's basically the volume of this shell right here. So we can take this equation and we can divide it by the volume, and I can do a little rearranging by kind of like flopping some things. So now I'm left with 0 is equal to minus Vz at z plus delta z minus Vz at z. And then if I'm dividing by delta r times 2 pi r, that cancels with both of these, and then I'm left with just a delta z in the denominator here. So what does this mean? Well, we're close to something looking awfully calculusy, right? So if I think about this calculusy, this is essentially the definition of a derivative. It's a derivative with respect to z, but because Vz could hypothetically vary with many variables, z, r, theta, and time, right? So in general, Vz could be a function of r, z, theta, and time. Vz could hypothetically be a function of all of these things. We say, hey, this is a derivative, but not an ordinary derivative that we're used to from Calc 1. This is instead a partial derivative. So we still have this minus sign out front. So now it's basically partial Vz with respect to z. So what does this mean? Partial Vz with respect to z is equal to 0. So this basically implies that Vz is not a function of z. So what does that mean? Vz is not a function of z. We basically assumed, and that's from this result. That's from this result right here. We said that Vz was not a function of theta because it was axisymmetric. We said it was not a function of time because it's steady. So that this basically allows us to conclude that Vz is a function of r only. So once we do this, this basically says Vz is a function of r only. And this basically affirms the 1D assumption that we were making here, right? So basically we're saying, hey, the only velocity that's non-zero is our z velocity, and that z velocity varies only with r. So that's pretty sweet, right? Okay, so there we have it. Conservation of mass. We affirmed that the flow is 1D. So we already did this. We did this. Now let's go ahead and apply conservation of momentum to this ship. Another thing that people do, sort of consistent with this dvz dz is equal to 0, that's basically saying that if I have some velocity profile at some point, let's say here, I'm going to get the same exact velocity profile at some point later on down the flow. Basically, you know, if I move with my z, I'm not changing the nature of my velocity profile at all. And sometimes people call this a flow that is fully developed. Which basically means it no longer varies with z. And oftentimes you'll find a case if in real flows with pipes, you might have a flow that is not quite fully developed close to the entrance of the tube, but once you pass some position in the tube, everything is pretty much sorted itself out, and it's going to be the same velocity profile that you get at any point downstream. So if you hear the fully developed assumption kind of popping around, you know, that's basically consistent with this line of reasoning that we've done here. All right, now, as promised, let's move on to conservation of momentum. And when we did the blood oxygenator problem, we needed to apply conservation of momentum in 2 directions. But now let's sort of just keep the vector form of conservation of momentum, and we'll see if we want to break it out into components later on. So conservation of momentum, d dt of an integral over the volume of vector velocity times rho times dv is equal to minus an integral over the surface of vector velocity rho v dot n dA plus the sum of any external forces, and we're keeping the vector versions, which is, you know, secretly this is all 3 conservation of momentum equations all in one. So take a moment now, pause and ponder. Can we right off the bat make any simplifications to these, to what we have here? Well, perhaps you can, sort of for the same reason that we did in conservation of mass. If our system is indeed at steady state, then this time derivative left-hand side goes away. What can we say about this term? Well, can we make any simplifications here? What does this term become for conservation of momentum? I'll give you a hint. Let's think about our results from conservation of mass. Right, so let's sketch my control volume right here. If I have this is essentially my ins minus outs that I have right here. What can I say about the momentum entering through this face as compared to the momentum exiting through this face if my z velocity doesn't vary with z? Well, if my z velocity doesn't vary with z, I might have some z momentum entering, or some momentum in general in any direction entering through this face. But if the flow going out is exactly the same as flow going in, my ins perfectly balance my outs for momentum. You know, if I have flow that doesn't vary with z, if I have the same thing going in and out, you know, stuff goes in, stuff goes out, and it perfectly cancels out in terms of this integral. Because this integral essentially counts for both the ins and outs, right? So if my ins and outs are going here, this essentially goes away because my flow is fully developed. My flow is fully developed. I have the same amount of momentum entering as exiting, so the net momentum entering and exiting ends up being 0. So what does this mean? Well, conservation of momentum basically says, hey, you know, I'm going to have some external forces on this control volume. So these external forces basically just need to balance out. So what is that going to look like? Well, we said external forces come in 4 flavors for fluidsy problems with control volumes. There's pressure, gravity, shear stress, and through solids that cross the control volume. Can we cross any of these 4 flavors of force out from the beginning? Well, yes, we can. This shell that we've defined right here, this shell is always going to be entirely within the fluid. Never does this shell, partially extend into the solid walls of the pipe. So basically, this shell is entirely contained within fluid. If the shell is entirely contained within fluid, then there are no solids that cross the wall of the control volume, so we can get rid of that. So now we're left with a slightly fewer number of things. So the time has come now to consider what component of this momentum we're looking at, or essentially what forces we're balancing. What direction, what z, r, theta, what direction are we balancing forces? So it turns out that a lot of times, if you're looking to derive a velocity profile, for example, a z velocity profile, it turns out that the most useful component of conservation of momentum is in the direction of flow. So when in doubt, start with the component where with the velocity, with the direction of the velocity that you're interested in. So we want an expression for vz as a function of r. So we're going to choose to look at z. We're going to choose to look at the z component of this momentum. So what does that mean? We now basically need to say, hey, is there any z force due to pressure? Is there any z force due to gravity? Is there any z force due to shear stress? And we already concluded that there wasn't any shells. So take a moment now, pause and ponder. Which of these might we need to keep? Which of these could we get rid of? Can we make even any more progress if we're just at this point looking at z momentum? Well, what are we going to need to keep? Well, we basically said pressure is going to be driving this flow, right? So we're going to have some pressure in the upstream phase here. We're going to have some pressure downstream here. So we might have different pressures on different parts of this control volume. And it turns out that pressure is actually going to be important for driving this flow. So we're going to need to keep this one. Gravity, well, we said we're looking just at the case where we have horizontal pipes. So I know a lot of times usually we put z in the direction of gravity, but it turns out for these problems it was useful to put z along the axis of the pipe. And we basically said if gravity is pointing this way and our pipe axis is pointing this way, then in our z direction we actually don't have any gravity. So we actually don't have gravity in the z direction because we assumed that the pipe was horizontal. And then, are we going to have shear stress? So take a moment now. Think, are we going to have shear stress that results in forces in the z direction? The answer is heck yeah, right? If we have velocity gradients in this r direction, then we're going to have shear stress. We anticipate having shear stress on these faces right here. So face 4 and face 3 on these kind of inner and outer faces of the curved faces of the control volume. So what does that mean? We're going to have pressure, we're going to have shear stress, and hopefully these two forces end up balancing out because we concluded from conservation of momentum that basically the sum of forces is now equal to essentially 0. So what does this mean? This reasoning right here basically says that 0 is going to be equal to the z force due to pressure plus the z force due to shear stress. And we better deal with that. So let's deal with pressure first. So I like to think about pressure acting on my control volume right here. So here's my control volume. So I'm basically going to have pressure, and if I'm worried about forces in the z direction, I'm only really worried about pressure on this upstream face as well as pressure on this downstream face, right? Hypothetically, I could have pressure pushing, pushing outwards on the inside of the ring or pushing inwards on the outside of the ring, but those are basically going to result in forces in the r direction. I'm worried just about forces in the z direction, so I'm really just worried about this upstream and downstream face of my little circular ring. So if I want to figure out my z force due to pressure, I consider pressure pushing inwards on this upstream surface and also pushing inwards on this downstream surface. So my x force due to pressure, well, here I'm at position z, here I'm at position z plus delta ez. So the pressure right here is basically p at z, and the pressure down here is p at z plus delta z. The relationship between pressures and forces is force equals pressure times area. So I can take pz, multiply it by the area of this face. I can take p at z plus delta z and multiply it by the area of this face, and those will give me the pressure forces. So what does that look like? Pressure at z. On the upstream face, this pressure pushes me in the positive z direction. So it's pressure at z times the area of this upstream face, which we already worked out was 2 pi r delta r. Imagining unwrapping this circular face into a rectangle. This pressure on the downstream face pushes me in the negative z direction, so I'm going to have minus p at z plus delta z times 2 pi r delta r. So this is my net pressure force, and I don't have any contributions to z force due to pressure on those other faces. So pressure, check. All right. Shear stress is going to be a little trickier. So I'm going to draw a slightly bigger version of the control volume that we have here. All right. So here I have my cylindrical shell. If I kind of did like a little breakout, like let's look at a little breakout of sort of a rectangle, right? So basically, if this shell is this ring right here, I'm imagining kind of cutting through, taking out a little rectangular section of the top of this ring right here. That's this orange bit right here, right? So let's look at this orange bit. If I think about shear stress acting on this orange bit, let me put my coordinate system right here. R and Z is like this. If I think about shear stress that's resulting in forces in the Z direction, I'm thinking about it acting on this face. I'm going to be thinking about tau RZ. So what does it mean? This is tau where it's acting in the z direction, and it's acting on surfaces that have a normal in the r direction. So basically this outer surface right here, I'm going to have some shear stress on, and I'm also going to have some shear stress on this inner surface. This inner surface as well, right? So tau RZ is going to act on this outside surface, and it's also going to act on this inside surface. So if I think about this orange ring right here, and I use the kind of goofy positive convention for shear stress that the textbook has, on the top, i.e. right here, I have tau RZ acting right here, and I would call this tau RZ at r plus delta r, right? Because if I say my inner position here is r, the position of the outside is r plus delta r. The outside position is at r plus delta r. So on this top, pointing in the negative z direction is tau RZ at r plus delta r, and positive shear stress on this bottom face is going to be tau RZ at r, and that shear stress would push us in the positive z direction by convention, right? So this is by convention here. So the force due to shear stress, I guess in the z direction, is going to be equal to, well, it's this shear stress times the area of this outer surface, and this shear stress times the area of that inner surface, but we need to be careful with positives and negatives, right? So let's do the outer surface first. Well, there's a minus sign out front because this tau RZ by positive convention is pushing us in the minus z direction, and it would be tau RZ at r plus delta r times, and so force is equal to shear stress times area. So what is the area of this outer face? Well, the area of this outer face, keep in mind this outer face is at a slightly bigger radius than that inner face is. So the outer face is at a radius of r plus delta r. So the circumference of this outer circle is 2 pi r plus delta r. This is the circumference. This is that circumference right there, 2 pi r plus delta r, and then the width is delta z. So it's 2 pi r plus delta r times delta z. So we have this. So this is tau RZ at r plus delta r times 2 pi r plus delta r delta z, and that's the area of this outer face. This 2 pi r plus delta r times delta z is the area of this outer face, and that shear stress is pushing us in the minus z direction by convention. And then we have plus tau RZ at position r times 2 pi r times delta z, where this inner circle only has a circumference of 2 pi r, so if I unwrapped that inner surface into a rectangle, it would be 2 pi r times delta z. So this is my force of shear stress. All right, a little messy, but here we go. So now I take these two and due to my conservation of z momentum, I can add them up and equate them to 0, because the force is perfectly balanced from conservation of momentum. So what does that mean? Well, what do we get? All right, well, before we actually get too far, I'm going to do a little bit of a cheeky thing with this z-force shear stress business here. And you know, this, I'm sorry to annoy you a little bit, but I was always annoyed when a professor was like, well, I sort of already know how to solve this problem, so I'm just going to give you a little trick that'll make our lives easier. So bear with me, I'm going to give you a little trick that's going to make this easier. So instead, if I notice, I can kind of imagine that this thing is sort of like, you know, this, I can kind of group this shear stress at r plus delta r and this r plus delta r. I can kind of group these two things together. And I can kind of group this tau RZ at r and this r right here. I can kind of group these together as well. So what can I do? I can basically say my force in the z direction due to shear stress, instead of kind of having these two things separate and these two things separate, I can kind of group these together as one quantity, and I can group these together as one quantity. So what is that going to look like? I'm going to call it minus the unit tau rz times r evaluated at r equals r plus delta r times 2 pi delta z plus the unit tau rz times r just evaluated at r. So this thing, you know, I could basically take this r plus delta r, right, and plug it in for r and plug it in for the shear stress at this position right here. So what I'm basically doing is, instead of saying, you know, evaluating these two things separately, I'm saying, hey, let's group r plus delta r and tau rz at r plus delta r together and just evaluate that whole quantity at r plus delta r. And I'll evaluate tau rz at r, and r, I'll take that whole quantity and evaluate it at r. And if I evaluated this at r, I would get this thing here, and if I evaluated this thing at r plus delta r, then I would get those two things here. And I, of course, don't want to forget my 2 pi delta z that I also have for this term. And it turns out that this is going to make our lives a little bit easier when we get to the calculus coming up soon. So what can I do? I'm actually not going to plug in this version, but I'm going to equate the sum of these two to 0. So let's go ahead and do that. So what does that look like? 0 is equal to, I can factor out this common term, so I can basically have minus tau rz times r evaluated at r plus delta r minus tau rz times r evaluated at r times 2 pi delta z. And then I can have my pressure term right here. I'm going to flip-flop the order of these as well and factor out a minus sign. P at z plus delta z minus P at z times 2 pi r delta r. So once I get to some expression that has like this, I have things that are looking like differences. You know, hey, can I move in a sort of definition of derivatives sort of direction with these? Why, yes, I can. Typically, when we get to this expression here, we go to the next step. We want to divide by the shell volume. So if I take these expressions and I divide them by the shell volume, what do I get? I get the following result. I get 0 is equal to tau rz times r evaluated at r plus delta r minus tau rz times r evaluated at r divided by delta r times 1 over r. And then minus p at z plus delta z minus p at z, all of this divided by delta z. All right, so here I have two things here. The next step, I can take limits as deltas approach 0, and this basically means things become derivatives. And the key thing here is they become partial derivatives. Partial derivatives, because hypothetically, you know, shear stress could be a function of multiple variables, as could pressure. So what does that look like right here? 0 is equal to partial with respect to r of the product of tau rz and r, right? So just in the same way that you know, earlier I replaced a partial derivative of this difference of things. Here this is a partial derivative of the product of these two, because I kind of grouped them together in this earlier step here. So now I have a partial derivative of a product, And I can't forget this 1 over r that kind of just hangs along for the ride. And then here I have this partial derivative with respect to z. So here I have it. All right, so last time when we got to a result like this, we said, hey, could we integrate? So last time we basically integrated, and then when we integrated, we got instead of getting a plus c, instead of getting constants of integration, we got plus some f of other variables, right? So instead of getting plus c, we got, when we integrated partial derivatives, we didn't get a constant of integration, but we rather got functions of all other variables except for the variable that we integrated with respect to. And then we applied boundary conditions to help resolve what this as of yet unknown function of other variables was. We're going to take a slightly different a different approach this time, right? We could do this approach here, but we're going to make a slightly different approach here. We're going to apply reasoning that tau rz times r, this sort of product things here, varies only with r. So if we can apply reasoning that tau rz varies only with r, then we can replace partial derivatives with ordinary derivatives. And then when we do ordinary derivatives, we will get the plus c when we integrate, and that will be a little easier to deal with. So, either approach is valid. Last time we did it this way, just to sort of show how to solve partial differential equations, but I think it's going to be a little bit more straightforward this way to see, hey, can we apply some reasoning? So instead of having this nasty partial derivatives with respect to r, can we replace these with ordinary derivatives? So, hypothetically, tau rz times r, this product could be a function of r, z, theta, or time. But let's hope that we can apply some reasoning to basically show that it's only a function of r. So, is it a function of time? No, because we assumed the problem was steady. Right? So in the same way that velocity doesn't vary with time, nothing about our problem should vary with time. Similarly, if the flow is axisymmetric, velocity doesn't vary with theta, but also this product of tau rz and theta should also not vary. Should also not vary with theta. Now, does tau rz vary with z? Well, let's go back to some of the conclusions we made earlier. If vz is not a function of z, and tau rz is based on z, if z is not varying with z, then tau rz also can't vary with z. So what does this mean? We basically said dvz dz was equal to 0, which basically means that if z velocity doesn't vary with z, then tau rz can't either. And this is basically, this is essentially an implication of our fully developed conclusion that we got earlier. Basically things shouldn't be varying with z. Once velocity doesn't vary with z, other stuff also shouldn't vary with z. For the most part. Spoiler alert, there's an exception coming up. So when we have our fully developed assumption, this basically gives us. So we basically said, hey, tau rz times r shouldn't vary with z, theta, or t. It should only be a function of r and, of course, other known constants, but basically only a function of r. So what does this mean? Instead of having partial derivatives here, this basically means that d of anything with respect to r or in this case, d of tau rz times r with respect to r can become d tau rz times r with respect to r. So instead of having partial derivatives, we now have ordinary derivatives. Why do we care about replacing partials with ordinaries? Well, that basically makes our integration lives a lot easier by now getting constants of integration instead of messy functions of integration. Whew. Success. So where does that leave us? We now have a slightly simpler differential equation that we're attempting to solve. So now 0 is equal to d tau rz times r dr, this thing times 1 over r minus dp dz. Now, last time we needed to, when we had two partial derivatives in our situation, we needed to apply a different conservation of momentum equation. Instead of doing that, I'm going to just talk about some reasoning with dp dz and some stuff that we observe experimentally. So if we have a pipe and we basically have some p in right here and some p out right here, and our z position is right here, if I wanted to plot pressure in the pipe as a function of z, my pressure would start at p in, and by the time I got to the whole length of the pipe, I would be at p out. And it turns out that there might be some goofiness right at the beginning of the pipe, but after that goofiness happens, pressure tends to vary linearly as we go down. And there's a very rigorous way to go about proving this, but basically the slope of this curve right here is dp dx. And for as long as we're not in this entrance region right here, within the fully developed region of our flow, d most things, for example, vz, d most things with respect to z equals 0, except for d pressure dz, which in this fully developed region is equal to a constant, is equal to just some known constant, right? So what is our sort of observation? In this fully developed region here, I'm sorry I didn't draw it as a real straight line, but our pressure basically linearly varies inside this region, right? So if pressure linearly varies, then its derivative is constant in this region, i.e. dp dx is a constant. And oftentimes, this dp dz constant, you can basically approximate dp dz as basically minus p in minus p out over L, where L is the length of the whole tube that you're looking to analyze, right? So, if I had some tube like this, let's sort of add to our list of knowns. If the length of this whole tube were L, and it were, indeed much longer than this section that I drew here, if I had some pressure at the inlet and pressure at the outlet, the pressure gradient, i.e. dp dz within this tube, dp dz within this tube would be minus p in minus p out over L. And we can see that this, dp dz has units of pressure per length, so pressure per length ends up working out here. And you could work this out, from a sort of y equals mx plus b type argument for what this line would look like. So what am I going to do? If I sort of make this approximation, I'm now basically going to treat dp dx as a known constant. If I could approximate it in terms of these given constants. So where does that leave us? We can now basically treat this as a known constant right here, and we have on our hands a differential equation, although dp dx looks intimidating, it's basically a constant, so we basically have a derivative and some constants. Can we solve this differential equation? Heck yes. So let's now proceed with trying to solve this differential equation. So if I think about trying to solve this differential equation, one strategy that I might use to try to solve this differential equation is separation of variables. So what might separation of variables look like? Well, you try to get all of your r-related variables on one side of the equation and all of your sort of numerator of the derivative things on the other side. So what's that going to look like? It's going to be d tau rz times r, where it's sort of d of this whole quantity on one side. And then on the other side, it would be dp dz times r dr. Right, so I've separated my variables, and now I'm looking to integrate both sides. Oh, I just realized I had a mistake. I lost a negative sign. I lost a negative sign. Oh my goodness. Way back here. In this step, I lost a negative sign when I carried this down. So this should have a minus sign. This should have a minus sign up front. And that means this should have a minus sign up front. So then when I bring this over to the right-hand side, I should be left with a minus sign over here on the left-hand side. Oh, shame on me. Shame on me for forgetting a negative sign. Here we go. So, sorry, I had lost a negative sign earlier in their derivation. So I did separation of variables. I can now integrate both sides, and I'm going to leave these as indefinite integrals. So when I integrate the left-hand side, if you integrate d something, you get whatever you had here. So now we integrate d product of tau rz and r. I'm now left with tau rz and r on the left-hand side. And then on the right-hand side, well, this is a constant that could be pulled out of the integral. So I now have dp dz, and then a minus dp dz. Then when I integrate r dr, I'm left with 1/2 r squared. And then I have plus, and in this case it is indeed plus a constant of integration, right? Because these were ordinary, this was an ordinary derivative. These are ordinary derivatives here, so when I integrated these ordinary derivatives, I get plus a constant of integration, not a function of integration like I got for last time when I was just integrating the partial derivatives before trying to analyze them. So what do I have? What do I have here? All right. So I have this result. What can we do? Spoiler alert, I'm going to anticipate actually integrating a handful of times in the development of this problem. So I'm going to call this constant of integration C1 because, spoiler alert, we're going to end up with a couple of other constants of integration as we move along. So before we get too far, I want to make those C's different from one another. So I'm going to designate this one C1. I can divide through by r if I want to, and also I can make progress here, right? So I now have some result that I got from applying conservation of momentum. So going back to problems here, we applied conservation of momentum, we got a differential equation. We actually did a little bit of progress in terms of solving that differential equation, so we definitely did number 3. We jumped ahead a little bit to problem number 5, but now we can go for number 4, right? So ultimately what we're looking for is a velocity profile. Here we got some equation for shear stress, but we can put in, hey, shear stress, we can put this in terms of a derivative for velocity profile. So let's go ahead and do this. Tau rz minus mu dvz dr. So we can plug that in for right here. So if we assume, so we can plug in our Newtonian constitutive relationship. And so that basically means that minus mu times r times dvz dr is going to be equal to minus dp dz 1/2 r squared plus as of yet unknown c1. So now I can take this equation, I can try to collect all my r's and r stuff on one side and my vz stuff on the other. So I can do a little bit of algebra, and I can basically get dvz dr is equal to dp dz times 1/2 r, times 1 over mu times 1/2 r plus it would be a minus c1 over mu r. Why do I get r in the denominator here? I had this r over here. I divided everything by basically minus mu r to kind of get stuff in. Some of it some of the r squared and the 1 over r cancel a little bit. I still have this, the minus signs cancel out here, but I still have the minus sign over here. So now I can separate variables and integrate. So I can bring dr over to the right hand side. I can integrate both sides. What do I get on the left hand side? I get vz. And then on the right hand side, what do I get? I get dp dz times 1 over mu times 1/4 r squared. If I integrate r, then I get natural log of r. So now I have minus c1 over mu times natural log of r. And when I integrate, I get now plus another constant. So what is that going to give us? That's going to give us an additional as of yet unknown constant of integration here. All right, so here I have it. I have, whoa, what have I done? I've gotten it. I've gotten vz as a function of r. Woohoo, woohoo. If only for these as of yet unknown constants. So we applied our constitutive relationship. We solved the differential equation. We integrated. Now the next step is to apply boundary conditions, and by applying boundary conditions, we can resolve these unknowns. So the way if I have two unknowns, then I'll need two boundary conditions, right? So two unknowns, then we'll need two boundary conditions. So think a moment now. These boundary conditions are places where we know a lot of information about the flow. So take a moment now and try to think, what are two boundary conditions? So pause and ponder. What are two boundary conditions that we can apply? Where are 2 points in the flow? Where are 2 points in the flow that we have the most information about what's going on in our system? All right, so the easy one is at this outer surface right here, right? Or at this outer surface of the pipe right here. We basically know that the fluid velocity has to be 0 right here, right at this outer surface, right? So what does it mean? That basically the z velocity evaluated at little r equals big R. That z velocity has to be 0. So at little r is equal to big R, which is the outer radius right here. The z velocity needs to be 0. So that's going to be one of our boundary conditions. other boundary condition is a little bit trickier, and it actually takes, it could take sort of two forms. So one form is that velocity needs to be finite, right? There's no such thing as an infinite velocity. So velocity must be finite. And what about this equation is potentially problematic? Well, particularly at little r equals 0, what happens if you try to evaluate this expression at r equals 0? Well, if you try to evaluate this expression at r equals 0, natural log blows up, right? If you were to plot what natural log of r looks like as a function of r, it has this negative asymptote as r approaches 0, and then kind of grows out like this, right? So natural log of 0 is actually negative infinity. So what does this mean? You know, we basically, the idea that velocity must be finite at r equals 0 gives us information about what happens here. An alternative to this reasoning that is, you know, potentially equally useful is we know that the max velocity must occur at the center line. Right, so if we have this pipe flow, you know, we know the max velocity occurs at the center line, and this max velocity occurring at the center line is basically equivalent to saying dvz dr evaluated at r equals 0 must be equal 0. So not that velocity needs to be 0 at the center line, but that the derivative of velocity must be 0 at the center line, and that's basically saying that there's a local max in velocity right at the center line. So that could help us as well. So what does this mean? Well, let's just proceed with this relationship right here. If velocity is finite at r equals 0, then this basically implies that the only way that we could get a finite velocity at r equals 0 is if c1 is 0, killing this entire natural log of r term, right? So this basically means that c1 is equal to 0. And it turns out that we would have concluded the same exact thing if we had applied this other idea right here. So what does this mean? We get a slightly simpler version for our z velocity. Vz is equal to dp dz times 1 over mu 1/4 little r squared. And we don't have this term anymore, so now we just have our plus c2. So usually one boundary condition helps you resolve one constant and another boundary condition helps you resolve another constant. Sometimes you might need to solve a system of equations with two unknowns. We can take this expression and we can evaluate it. We can now go ahead and apply this first boundary condition. We can attempt to apply it to this. And what do we get? So at r equals 0, we know that vz equals 0. So what does this mean? 0 equals, oh sorry, at little r equals big R. So we can plug in a big R for little r right here. dp dz times 1 over mu times 1/4 big R squared plus c2. Well, what does that mean? That basically means c2 needs to be equal to negative this. And if c2 equals negative this, then we can plug it back into this equation right here. And c1 we can plug in 0 right here. Or I guess we can plug in c2 equals negative this. We can take this result right here, and we can plug it back in for c2 right here. And that means we can get vz entirely in terms of knowns. So what does that look like? Well, you can write it out. It turns out that, you know, because both c2 has this dp dz 1 over mu 1/4 in it, we can sort of simplify things just a little bit when we get to our final result. What does it look like? We get vz is equal to minus dp dz times times 1 over mu times 1/4 of big R squared minus little r squared. So I did some flipping around and some minus sign business, but we can basically get to this result right here. All right, success. So I would say we successfully solved the differential equation, integrated and applied boundary conditions. So what's our next step? Well, our next step is to do a couple sanity checks on this result. So if we think about a couple of sanity checks, one check that we like to do is units, just to make sure that we got everything. VZ should have units of meters per second. And we hope that the units on the left-hand side match the units on the right-hand side. Pressure has units of newtons per square meter, or kilogram meter per second squared per square meter. So dP dz is kilogram meter per second squared per square meter per meter. 1 over mu, well, mu has units of kilograms per meter second. So 1 over mu would have units of meters second per kilogram. 1/4 is unitless, and then both r squared and r squared would have units of meters squared. All right, so let's cross our fingers and hope that a lot of this stuff cancels out. My kilograms in the numerator cancel with kilograms in the denominator. This meters in the numerator cancels with that meters in the denominator. This meters squared cancels with that meters squared right here. And then I have a 1 over seconds squared right here. And that would cancel, or I guess just the squared would, sorry, I keep this seconds, but the squared cancels with this seconds right here, and I'm left with meters per second. So we're okay. Whew. So baby you know who is now going to be very pleased that the units line up on both sides. The second sanity check that we like to do is how do these variables on the right-hand side affect what's going on with the left-hand side? And then another sanity check that we can do is to make sure our boundary conditions make sense. So what are our boundary conditions? Well, if I evaluate this at r equals 0, you know, I'm essentially subtracting the smallest thing here, right? So at r equals 0, I get my max because I'm subtracting 0 instead of subtracting something positive away from this velocity right here. So at r equals 0, I get my max velocity. At r equals big R, I get Vz is equal to 0, right? So if I sub in little r equals big R, you know, this whole term basically cancels away. This equation is essentially of the form of a parabola, which is consistent with this parabolic flow that we've been talking about all along. So that's good. So it's parabolic. But you might be saying, hey, wait a second, what's going on with this minus sign out front? What's going on with there, right? Wouldn't I expect that, don't I expect z velocity to be positive? So what's the big deal with this minus sign out front? Well, this minus sign out front is sort of used in conjunction with this dp dz that we have right here. So if I truck back in the notes to the expression where I had here, sorry, this is dp dz. If I have here, dp dz is usually less than 0, right? If I have a higher p in than my p out, as I go forward in z, I drop down in pressure. So usually dp dz is negative for pressure, for flows where where pressure drives the velocity, you know, drives the velocity through the pipe, right? So dp dz is less than 0. So if a minus sign and a dp dz is less than 0, then this whole product together is positive. So I have a positive thing, and then a positive thing right here. So when dp dz is negative, I get pressure, I get a positive z velocity, because basically I'm dropping pressure as I go down in the pipe to drive that flow. So although there's a minus sign out front here, dp dz is usually negative, so we end up with a positive z velocity. so that makes sense too. So basically, as the magnitude of our pressure gradient goes up, then the magnitude of velocity grows up. But dp/dz is usually negative, so that's why we have this minus sign out front. As viscosity goes up, the velocity goes down, and that makes sense, right? If we're trying to pump a more viscous fluid with the same pressure, then we're going to get less flow. And this r squared and r squared, we already talked about how it matches at r equals 0 and r equals r. So all this works. Great. Success. We feel good about ourselves. So thanks for watching. I hope you enjoyed this lecture. Good luck with your study of fluid mechanics. Take care.